This is video number 6 in our series Topics in Tensor Analysis. In this video, we're going to look at more of the properties of contravariant vectors and contravariant tensors. A reminder that the playlist for all the videos is featured at the website at digital-university.org. Okay, here we have sketched out just sort of a generalized curvilinear coordinate system, where here is one curvilinear coordinate axis, u1, another one u2, and another one u3, and here is some point P out in space. And then we have a set of Cartesian coordinates with a position vector r. Now, in our previous videos, as a specific example of a curvilinear coordinate system, we sometimes used spherical coordinates as an example. And this was the graphic that we had used previously. Now here, for the spherical coordinates, the position vector itself, or more rather, the magnitude of it, that is one of the curvilinear coordinates for the spherical coordinate system, along of course with theta and psi. Incidentally, if we were to just make a general sketch of the spherical curvilinear coordinates, what would it look like? See, the phi goes like in this direction, then that's theta, excuse me, and that goes in this direction, and the psi goes in this direction, and r goes like this. So just a general sketch of the spherical curvilinear coordinates would be something like this: theta, psi, and then the position vector r. That would just be this would be for the theta, the psi, and the position vector r. That would just be a very generalized sketch for spherical coordinates. But for our discussion, we're just going to consider, in general, a curvilinear system like this. And again, the axes are numbered 1, 2, 3. We could have any number of them. We're just going to restrict ourselves to 3 in this video, and they're designated with superscripts. And likewise for the Cartesian coordinates, x1, x2, x3. Now, these are the unit vectors, the Cartesian unit vectors. These, of course, are tangent to their respective coordinate, and they're of unit value. And notice that the numbers for these are designated with subscripts, and we are underlining these so that we don't confuse them with this situation up here. Now, here we have the u1 coordinate axis, the point P, and this is a tangent vector, a vector that is tangent to the coordinate axis u1 at the point P. And this is a tangent vector, again tangent to the u2 coordinate axis at the point P, and this is tangent to the u3 coordinate axis at the point P. And here is our position vector r. And again, these tangent vectors we label with lower numbers, even though the axes themselves are labeled with upper numbers. Now, in general, of course, we could say that the position vector r, we could just write down very simply what a just write it down in general form of Cartesian coordinates for the position vector r. It would just be x1 times the position vector e1 plus the x2 coordinate times the position vector plus the x3 coordinate axis times that position vector. Now, we're assuming here that we know how to transform from the curvilinear coordinates to the Cartesian coordinates, just like we did with the spherical coordinates, where with the spherical coordinates, if we knew the value of the Cartesian coordinates, x1, x2, and x3, then we could determine the value of any of the spherical coordinates, r, psi, and theta, by using these formulas. Likewise, if we know what r, theta, and psi are, then we can determine what the Cartesian coordinates x1, x2, and x3 are. So, for our generalized system, that we're assuming that if we know what u1, u2, and u3 are, we know the function that's going to give us x1. Just like for the spherical coordinates, we know the function that's going to give us x1. And likewise, if we know u1, u2, and u3, we know the function that's going to give us x2, and the function that's going to give us the Cartesian x3 coordinate. Or, if we know x1, x2, and x3, the three Cartesian coordinates, we know the function that will give us the u1 curvilinear coordinate, and so forth. So, that means then that the position vector r, we could write it like this. x1, we know the function of u1, u2, and u3 that gives us x1. Same thing for x2, and the same thing for x3. So that means then that if we wanted to, well, first we can write dr, a differential displacement of r. We could write that very simply just by using elementary calculus. That would equal the partial of r with respect to u1 du1 plus the partial of r with respect to u2 du2 plus the partial of r, try to keep things in focus, with respect to u3 du3. And again, we can take these partial derivatives because we can express r as a function of u1, u2, and u3 by using our transformation equations. So taking these derivatives is no problem. Now, this tells us then how the position vector changes with respect to the u1 axis when everything else remains constant. So this partial derivative that is that tangent vector E1. Likewise, the partial of r with respect to u2, that is that tangent vector E2. Let's just get that diagram here. So we had a position vector r. We take the partial of r with respect to u1, and that gives us that tangent vector E1. Take the partial of r with respect to u2, and that gives us the tangent vector E2. Take the partial of r with respect to u3, and that gives us the tangent vector E3. And again, we can take those partial derivatives because we can express the position vector itself as a function of u1, u2, and u3 by using our transformation equations. Now, if we have, say, some vector, we can just draw it in here, I guess. Say that here we have some vector A. So our vector A will have components along U1, U2, and U3. Now, these partial derivatives that we took to get E1, E2, and likewise to get E3. These are tangent vectors, but they're not unit vectors. If we wanted to get the unit vector, we would have to, whatever this is equal to, we'd have to take the dot product with itself, and take the square root of that so we get the magnitude of it, then divide this by the magnitude of that. In other words, find out what this is. Then divide this by this, and that would give us the unit vector E2. Divide this by the magnitude of R, whatever the magnitude of that vector is, divide it by the magnitude of that, and that gives us the unit vector. We didn't do that because in most textbooks you'll see it's just written simply as E1, E2, and E3. That is, they do not work with the unit vectors. They work with the tangent vectors, so that if we have a vector A, we can say, well, vector A, that's going to have a component on the U2 axis, a component on the U3 axis, and some component also along the U1 axis. So vector A could be written like this then. We're going to have the E1 tangent vector, and that we multiplied by some number. Let's just say A. Right now we'll just write it like this, A1. So that, see, here's our vector A. That's going to have some component along the U1 axis, and whatever that comes out to be, that can be expressed as the tangent vector times some number. And that's what we showed right here. Plus, our vector A will have a component along the U2 axis, and that would be equal to the tangent vector times some number will give that component of A on the U2 axis. So right now we're just going to write it like this. And likewise, for U3, vector A is going to have some component on the U3 coordinate axis here, and that would be equal to the tangent vector times some number. So vector A, expressing vector A simply as its components along the U1, U2, and U3 axis, we could write like this. But in fact, we don't write it like this. We write these as superscripts. We write it like this, and I'll explain why in just a minute. But the vector A is written like this. And the reason for that is this, is that here we have a vector. We express this vector as summing its components along the coordinate axis. The components along the U1 axis, the components of A along the U2 axis, and the components of vector A on the U3 axis. Okay, if you express the vector like that, then if you transform from our U1, U2, U3 coordinate axis to another different coordinate axis, and you know the transformation equations, then the vector transforms analogous to a displacement vector transforms, as we explained in the first video. In other words, if you have a vector and that vector is written as the sum of its components along the coordinate axis, then if you transform from here to a different curvilinear coordinate system, then that vector transforms as a contravariant vector. And as we explained in the previous videos, contravariant vectors are written so that their components have superscripts. Now what we haven't explained is this. Okay, let's just say then that we have a general curvilinear system like this, U1, U2, U3, and so forth, and we have a different one here. Well, this might be V1, V2, V3, and likewise for these axes. And we have a vector A. Okay, now these are U's and these are V's. Let's make these W's so we don't get confused. So here we have the U coordinate system, here we have the W curvilinear coordinate system. Our vector, if it's expressed as the sum of the components along these different axes here, then if we transform from here, and we know what the transformation equations are to go from U1 to W1, and we assume we know what the transformation equations are to go from W1 to U1. If our vector is expressed as the sum of components along these different coordinate axes, then that vector, if we transform it from here to here, will transform as a contravariant vector. So that's why when we write these components here, we use these superscripts, as we explained in the previous videos, that for contravariant vectors, that is, those that transform an analogous way to the way displacement vectors transform, as we explained in our first video, their components have superscripts. Now, we haven't explained yet why this is so. We haven't explained, well, why is it then that if we have a vector here and its components are expressed, or it's expressed as the sum of the components along these different axes, if I transform from here to here, that's going to transform as a contravariant vector, not as a covariant vector. We haven't explained why that's true yet. We just stated that it is true. In the next video, we'll show why that is true. Now, we have just a few minutes left here. Let's say that this is our set of coordinate axes, U1, U2, U3. Here's a vector A, and let's just consider the U2 and the U5 coordinate axes. So vector A could be written then as the sum of its components along U2 and along U5. So we could just say that A, ignoring the other axis for the moment, is equal to A2 E2 plus A5 E5. Again, just simply expressing A considering the U2 and the U5 axis. And then if we transform this to a different coordinate system, that would transform as a covariant vector. Now, these lines that you see, this one is not tangent to the U2 coordinate, it's perpendicular to it. And this one is perpendicular to the U5 coordinate axis. Well, our same vector A, if we wanted to, we could express that then as the sum of components on this orthogonal and this orthogonal. That would be another way of expressing it. And if we do that, and then we transform to a different coordinate system, now it transforms as a covariant vector. Now it transforms analogously to the way a gradient vector transforms from one system to another, as we explained in the previous videos. Why that's true, we will show that in the upcoming videos here. But what we'll do in the next video is show why it is that if our vector A is expressed as the sum of components along the coordinate axis, when we transform to a different curvilinear coordinate system, it will transform as a covariant vector. And we'll show why that's true in the next video. So join us for that video, and we'll continue on here with our discussion.